We are on a never-ending quest to do something better, something nicer. Well, this is not that case. This is gonna be the first component for my engine that I've been working on for 20 years, and when it's gonna be done 20 years from now, you guys gonna look back and you're gonna say, oh, I saw that guy when he made that first part. Welcome back to the shrine. Today I'm gonna talk about tappets or lifters for engines. So for starters, here's a lifter. This is from a Harley, some kind of engine from the late 90s, Harley Davidson. You can see it's hollow inside to compensate for the valve lash, so there's some springs and valves and pistons and some other stuff inside. The lifter I'm working on is half of this size, and it's due to constraints. So when I started to design the lifter, I was trying to figure out how I'm gonna make the part, how I'm gonna machine the part. And so the initial idea was to take an end mill, come in and create this pocket. So this is the pocket where the roller sits, and when the cam is passing by, it's gonna push the lifter one way or other. So when the cam is coming through like this and it's pushing the lifter on this back side of the lifter, you know, it's gonna slide against the wall and we're gonna have a lot of pressure. So this is hardened steel, ground and polished, and it's going against aluminum, and I need this surface area here to minimize that pressure. So I cannot make an open lifter that doesn't have the pocket. So in one word, I cannot just come in with a mill and cut it this way, you know, so that it's open at the edges because of the high pressure here, according to my calculation. Well, this is the first one I'm working on, but I trust my calculations because I calculated my calculations. Well, anyways, I have a roller just like this. It's gonna sit in there. There's gonna pin, retain the roller, and I need to make this cavity inside the lifter. And so again, my original idea was to come in with an end mill just like so, and then machine this cavity. Initially, you know, coming in with a large enough end mill and then coming in with a smaller one and basically fine machine it. Well, the problem with that is that the end mill would have to be really small, so about 1/8 of an inch size. And so when the end mill comes in, because the hole or the socket is deep, the end mill is going to bend out. So I cannot apply high feed rates. Even with low feed rate, it's not going to work. Additionally, if I machine this pocket, there are going to be artifacts of the machining, and those artifacts most of the times would be a sharp corner. So sharp machine corners and high cycle components don't mix. It's just not a good start for a high cycle component. So after months of consideration, I decided to go ahead and basically forge this socket. And so the forging tool would come in, this would be heated up. The forging tool comes in, forges the part, and when it retrieves, it leaves this socket behind. As you can see, this is most likely a cast or powder metal part, which is heat treated and machined afterwards. Well, I'm a small workshop, basically a garage mechanic, if you will, and I don't have access to that kind of machinery. So the idea is take a piece of rod like this, 8620, come in, machine some kind of starting pocket, and then heat this up in a kiln to forging temperature, and come in and pound this thing in. Simple, right? And then just do the machining after that. Well, this is where I'm right now. As you can see, I have a stub here that I machined on my CNC mill. Actually, this was the first part. I bought the same piece of acetal or Delrin, and I just tested the tool paths and the trajectories on it. Make sure if I crash the part, you know, it's not going to be detrimental to the CNC machine. So this part is the first part that was machined on my CNC. You guys seen videos of fixing different aspects of the CNC. So here's one part that I tried to machine with a 2-inch long 3/8 diameter roughing end mill, and you can see that the surface is pretty rough. You can see the first boo-boo here. So that was the first tool breakage, and accordingly, because we are in the shrine, right, I created a boo-boo urn. So this is the proper place for all the boo-boos in the future. So the machine cut this, but it was squealing, so I went back and changed the setup, used a shorter tool holder and a shorter stubbier mill, and so this became the second part. As you can see, it's got a nice smooth finish on it. So the mill did a good enough job. All these were manufactured from this piece of rod. I just cut them off as I progressed with the different you know, machining sequences. And afterwards I created this tool. So all this tool is basically the end mill comes in and it cuts it this way, and then I turn it 90 degrees and it cuts it this way. It's really simple to describe, but in reality it took months of carefuling and consideration, and laying out the trajectory in Creo, then converting the file into G-code. I have a Creo license at home, bought it years ago. So the tool has 2 degrees of taper on all sides, and that is to be able to remove the tool from the billet that is being forged. So if I don't have that draft, I'm running a chance of locking up the hot component that I'm just forging into this. You can also see that there is some machining artifacts here in this area. So first I machined this contour, and then I turn it 90 degrees and I machine this contour. So when I was machining this second contour, the center of the universe relative to the center of the component wasn't set up properly, and so the mill came into it a little bit. I mean, it was just scratching the surface, but nonetheless it made this flat, and I'm not happy about it. So after all this, I came up with a simple and ingenious design to ram the tool into the part, and my idea was to use a stamping tool. So here's the stamping tool I purchased. As you can see, it's just a standard, I'd say 6-inch, 5-inch by 5-inch stamping tool, and this can slide up and down like so. Maybe if I set it to the side, so you can see it's sliding up and down. So these 2 pins are making sure that the top part is parallel to the bottom part, and my idea was to position this part right there in some kind of socket and put the bottom part here and then press this with a press. Well, I've got a hydraulic press at home and I did some tests, so pressing it down for basically 5/8 of an inch or 16 millimeters, that's how much I need this tool to penetrate that part. It took almost a minute of ka-chunk, ka-chunk, ka-chunk. And I wasn't happy about it. I was honestly thinking that this will just lock up together and it's not gonna work. So I went to plan B. So at this point I'm gonna start machining the first component, which is gonna be the RAM. And I've got a print here, and even this print is not up to date, and I talk about it a little bit later. But as you can see, it's got this nose section, and that is what I'm going to machine on the mill in two different planes. And then this back section, I originally designed a 1/2 inch 13 threaded hole, which I'm not gonna put the threaded hole. I think it will weaken this entire section. And I've got some 01 tool steel, as you can see, but the ends have only a saw cut. So the first thing is to throw this up on the lathe, both sides, and then basically put it in a mill and then butt this end against a hard stop, come in, machine it this way, and then turn it 90 degrees, butt it to this top, and then basically come in and machine it again. So let's go and start using the CNC mill and the lathe. Let's do a measurement. This flat to flat side, you know, excluding the taper, should measure 18.8. So 18.8, 46 on the top, 18.8, 937 on the bottom. Again, it's 827 on the top. So there's difference between the top and the bottom, which means that the tool is bowing out, it's bending. So I'm gonna come back and do a couple more finishing passes. ended normally. That's what I was looking for. Look at all the chips that the CNC created. That is 01 tool steel chips, the finest 01 tool steel chips. So here's the part. As you can see, the cutter is still intact. It's not chipped. However, this cutter didn't survive the gauntlet. I think there was a point where the G-code was pushing it a little harder when it was chipping out these areas here. So we're gonna go and populate the boo-boo urn. There you have it. Everything goes in its right place. Well, the day started with buttons not responding to my input. Not sure what happened, but I found an old keyboard. You can see the patina on it, which has the same connector, so it's saved the day. I think this is what you call fresh from the mill. This is first look after machining. So we are looking at this size here, this thickness, supposed to be, let's see, 806. So 8.17. So let's say that's 100 microns off. Let's have a look with the micrometer. So the size is 8.183. So it's basically off by 123 microns. And I've done numerous finishing passes, but despite that it's off by, let's say, 2 or 3 hair thicknesses, 8.185. So the code calls for 8.06. As far as the edges, they are sharp. The surface roughness is not as nice as it was previously. Most likely because I broke that previous tool and I found a similar one and I used that. You can see the machining is not the same. The sheen is not the same on both sides. When I finished the first finishing pass, I put some dichrome on it and then I came back with another finishing pass, and you can see this was the top here and it didn't take the dichrome off, but it took it off here. So that means in an earlier machining pass the tool was bending in this area. I'm not even sure about the size of my tools. I just pulled something out of the box. It looked carbide, looked good enough for this job. And also I use the same tool for finishing and roughing. It's kind of hard to measure this size, so it's 903. That's 896. So essentially it is centered. It is centered relative to this axis here. So that is the punch. That is the tool.